What is a line of gravitational force? We draw all this. We draw all this line FG. What does it represent? What does it do to the object? That's what they're asking. Second one, they ask, why is the field strength approximately constant? Field strength near the Earth, 9.81. Why? A gravitational field may be represented by lines of gravitational force. So we say, oh, this is a very big mass. If we say there is a mass here, you got some field lines around it. Okay, we don't see the field lines though. But let me finish drawing them all first. Like that. So how will we use gravitational force to represent it? That means you will have some mass here. You could draw lines of gravitational force to show that it will be attracted to this thing. So what's the arrow do? It just show you where the mass will go or the direction of force on the mass. So here you can explain it as this line of gravitational force, this purple color line, is the direction of gravitational force on a small test mass. What am I writing? Test mass, yeah. That's why we draw it in such a, and that is parallel to the field at that point. So you got to think of something like this: force on test mass, direction where a particle will move, a small test mass will move. Okay, you must talk about mass. This is gravitational force, so must say mass. This is B1. Direction of force on a small test mass. We go to part 2. By reference to lines of gravitational force near the surface, explain why gravitational field strength near the Earth's surface is approximately constant. Usually we say roughly about 9.81. Why near the surface only constant? So if you look at the top left picture, this is what we call a radial field. Because all the lines that I draw is like radius coming out from the middle, so we call radial. For it to be constant, you need a uniform field. Like the one in electric field, then you got 2 plates and then the field line is like that. This is called uniform field. Equal spacing between them. How is it possible to have a uniform field in the planet? Actually can, if you zoom in on your scale a little bit. So now if you go outside your house and you look at the road is flat. Assume the floor is flat, the ground is flat. You don't stay in a mountain area. But I thought the earth is curved. Isn't the earth supposed to be a flat earth? Because I look out, the fields, the green is all flat. Makes sense, right? Last time people look around, looks very flat. Earth is flat. Flat earth theory. Yes, it is true. The earth is flat if you zoom in to one tiny section on the earth. Doesn't mean the whole earth is flat. It means that at your place where you are, the earth is flat. So on a grander scale of things, if I zoom in a bit, I see a curve. It's starting to look a bit parallel now, the fields. If I zoom in even more to, let's say, like right here, your spot in the house is pretty much a flat piece of land. That's the floor. And at that point, the gravitational field strength will be constant because the field lines are pretty much the same distance parallel to each other. That's because you zoom in, zoom in, zoom in. If you zoom out, then you see a circle. So how do we explain this thing in a sentence? First one, you talk about radial. So the lines are actually radial. Radial at surface of the earth. It's not uniform, it looks uniform, but it's actually radial. Every single line of this is perpendicular, 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 perpendicular. You also can draw perpendicular, 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 or perpendicular, radial. Then how? Near the Earth's surface, how do we describe this thing? You zoom in, it's almost flat. Don't write like that. That's not the physics term. So you can say that near the surface, what is my writing? Near the surface, lines are approximately parallel. If you zoom in a lot. So this is this first part. Because, must explain, right? So must say because h, the height at which you travel, height is very small compared to the radius of the Earth. So that means if I'm just throwing a rock from surface up to, let's say here, this small change in height, very small compared to the radius of the Earth. So on scale, it looks constant. G is 9.81 everywhere, no matter where you go near the surface. So the last point, you need to say, what does it mean? When the lines are parallel, gotta add on. So this means that the field strength near surface is constant. That's how you can talk about it. So there's three main ideas here that you will need to mention. The first one is talk about radial, the nature of this force. The nature of this field is radial. Go out like radius. That's number one. Then you talk about lines being parallel. There's my lines. Lines approximately parallel because why? Of the scale. How to talk about scale? H is small compared to radius of the Earth. This is B1. So what does parallel line mean? Parallel. This means that field strength near surface is constant. So this is making the link that, roughly 9.81. Everywhere you go near the surface, you can't go too far really. So this is the last point. Okay, that's how you can talk about this point right here. So next time if you meet a flat earther, they say, the earth is flat. Yeah, you can say, yeah, you are correct. Only on our scale though, where we can see, as far as we can see. If you play Minecraft, there is this interesting phenomenon. The Minecraft world is supposed to be flat, but they try to adjust the graphics such that if you can see very far, your view distance is very far, you will sort of see a curve effect because they purposely shape it in a way so it looks curved. But actually the Minecraft world is just, cube, 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 cube. But if you go really high up in a tall tower, crank up your view, and you look very far, it looks kind of curved. It's kind of a visual effect to create the illusion of a curved surface in the Minecraft world. So anyway, this is our Earth lah. Interesting observations that people made last time. All right, let's see. Okay, if you crank up your view distance, maybe just to see far, but after that the lag is just, I don't know, computer lag, server lag. If you have a gaming computer, no problem. Default is 32 chunks. Wow, okay lah. Alright, see the last part? This one you have to do some calculation already, no more writing. So now you have a moon. That's our big mass. A uniform sphere of diameter 3.4. And a very big mass. Moon has no atmosphere. So no atmosphere means we don't care about air resistance or friction. Energy lost due to friction. We don't worry about that. Which is kind of nice. During a collision with the moon with a meteorite, boom, a rock is thrown vertically up from the surface of the moon. So the rock comes up. And this rock starts off with a speed of 2.8. Assuming that the moon is, by itself, no other force or field around it, determine whether the rock will travel out forever, escape freedom from the moon, or it knocked off already and then return to the moon's surface. You find it hard to imagine what's going on, perhaps practice drawing to help you visualize. You have a moon. Aiyo, why my moon always? No, never mind. You have a moon. You have a rock. This rock got hit off with a certain velocity, 2.8. The question is this velocity enough, initial velocity, enough to let this rock travel into outer space? Or will it just go up and then pew, go back to the Earth, go back to the moon's surface? How do we know if it's enough or not? So I'm going to give you a head start. This is 4 marks hall. 5 minutes lah. 5 minutes to try out some methods. See how would you know if this is enough to escape? Tip, think of conservation of energy. You throw something up into the sky. Is it enough energy to overcome the gravitational potential energy? Okay, let's see. So what is happening here again? A rock is flying to outer space, right? Do you have enough velocity to escape the planet's negative potential? Well, because everything is attracted to the planet. You need to go, really need a lot of energy. So this is a question about escape velocity. If you watch the lecture video, do you have enough energy? So the question is, as you travel from surface of the moon with a big mass, travel out to distant space. When they refer to that to distant space, really means like infinity lah. So your tiny rock travel, pew. You see in cartoons, the good guy hits the bad guy with a super powerful punch. Whoopsha! Then the bad guy flies into the sky and ding, you see a star appear in the sky. That's a cartoon animation lah. But basically we're saying you have enough energy to go to R roughly infinity. At infinity, at least you should reach 0. So 0 velocity at infinity. At the end. So this is V0. Okay, what is the GPE at infinity though? So at the surface, you have some potential. So you have some potential energy. So here you have some potential, which is some negative, don't know what lah. When you travel very far away, this is going to have some potential that is 0. Or the GPE with reference to infinity, 0. 0, 0, 0, 0, 0. Very nice. I like it. So we're going to set up the equation for conservation of energy right now. So you have kinetic energy to start off, 2.8. We need to see if that's enough or not. So the change in kinetic energy, you're going to be decreasing, right? You lost KE. Loss of kinetic. You move slower and slower because someone's stopping you. The moon says, come back here. Where are you going? Then GPE, there's an increase. Gain or increase. Because remember, our potential graph looks like this. The further you go away, the more closer to 0. And 0 is bigger than negative. This can be a GPE or potential graph. Okay, so you're traveling from this point away, going to a higher potential. So increase on. You lift something up, higher potential. Then we need to plug in all the values we know now. So KE, which one to minus which one? We generally just take the larger one minus smaller one. So let's say we don't know what V here. You want to find the escape velocity. What should be the minimum? This is probably bigger, so we can say half mv squared. The energy in the beginning. Okay, here's some KE here. And when you go all the way to the end, you stop moving, there should be no more KE. So half mv squared minus 0. Just take the bigger one minus the smaller one. GPE change. Which one is higher, which one is lower? You have to look at the graph if you feel confused. Okay, you start off at the surface here, it's very low GPE. When you go to infinity, there is high GPE because you see the graph going up, high. 0 is higher than a negative number. So we're going to take the bigger one. So at infinity, that will be zero energy. Because of, we define infinity, 0, minus at the surface. So at the surface here, you have an energy which is gmm over r. Radius of the planet, we can use big R. Now, if you're like, Miss, where did this equation come from? Never see before. God, it's derived. Derived from the potential equation. So EP, not GPE, is m times phi, right? And phi is potential. So m times negative gm over r. That will give you this, negative gmm over r. That's where it came from. I just skip a step. All right, so now you plug in everything, can rearrange already. So half mv squared equals to gmm over r. But m and m here can cancel out, so that's really nice. Then we have left is half v squared equals to, let's plug in the value, 6.67 times 10 negative 11. This is a constant. You can use calculator to find or look at the data formula sheet. Okay, mass of the moon. Moon. Here, this is big, super big mass. This is going to be 7.4 times 1022. Radius, because we are starting off at the surface, we need to know what this radius is. They give us diameter though. Why so tricky one? In kilometers are more. Kilometer. Please remember to convert your kilometer. So we're going to take half of the diameter. 3.4 times 10 to the 3 kilometer. Must remember this. This is your diameter. Okay. So if you use this method to prove and check how much velocity you need to escape, we call this the escape velocity. This will be about 2.4 kilometer per second. But if you get here, don't stop there. You need to explain something. Because how does 2.4 relate to the 2.8? They say your rock fly away with 2.8. So you must have this. So what does this 2.4 mean? Let's write this out. So 2.4 actually is the minimum speed needed to escape the planet or escape the moon. And overcome the negative GPE of the planet. So you need at least 2.4. We have 2.8, more than enough, no problem. So I think we won't see this rock again. It's gone. It's going to go to some distant universe. So you need to write a concluding sentence though to compare. Here's one example you can say. So you say the rock, because because is the 3 dots the other way. So because the rock has 2.8 kilometer per second, we did a quick check, which is more than the minimum escape velocity, more than 2.4 kilometer per second. Therefore, 3 dots pointing up. It has enough kinetic energy, or just energy, to leave the moon. For distant space. Distance. Wait, no. Distant. T-A-N-T. Distant space. This is how you conclude, just in case. So this is one method to compare the velocity. You need at least this velocity to have this amount of energy. So this is a 4-mark question. Wow, quite long. First one is if you got equate half mv squared with the not mgh, because you are traveling very far now, cannot mgh already. Mgh is only on the surface. Half mv squared equals to gmm over r. This is the first one. C1 for equating. Second one, if you sub in the correct values, half of the diameter, 6.6, and the mass. And lastly, if you get 2.4 or some value, this is the compare velocity method, and you write a statement comparing 2.4 with the 2.8. That's B1. Okay, so far? So this is how you can check. If you want to do space travel, you gotta check. Enough energy or not? Make sure you got enough petrol, enough fuel. If not, cannot. You go up, you just drop back down. Like a basketball. Throw it up, comes right down. Not enough energy.